So we've got Nathanael Arkor today talking about the relative monad theory correspondence. So
thank you very much, and thank you for the invitation to speak. So today I'm going to be talking about some joint work with Dylan McDermott on the relationship between algebraic theories and monads. So what's known as the monad theory correspondence. And I gave a talk at CET in the summer on part of this topic. And so there's going to be a small overlap of maybe 5-10 minutes if you saw that talk, but the rest should be new. So this is the outline of the talk. I'm not going to go through it in detail, just to give you some idea of what I'm going to be talking about. But first of all, I'm going to give some context for the problem I'm interested in and why we care about it at all. So first of all, what is the monad theory correspondence in categorical logic? Well, we're going to start off by defining an algebraic theory to be an identity objects functor from F, which is the free category with strict finite coproducts on a single object. And we're going to ask if this functor preserves finite coproducts. And conceptually, this represents algebraic structure. I'm not going to go into the details of how, but we should think about this as representing some structure like a group or a ring or something like that. And on the other side, we have sifted co-continuous monads. So first of all, we're going to say that colimit in set is sifted if it commutes with finite products. And we're going to say that a monad on set is sifted co-continuous if it preserves these colimits. And these are the same as what are known as finite free monads on set. So finite free monads are those that preserve filtered colimits, but in the case of set, finite free monads and sifted co-continuous monads are the same thing. And the classical monad theory correspondence says that these, the categories of algebraic theories and the category of sifted co-continuous monads on set are equivalent.
So what is B there? What is the B there?
The B is just some category with finite coproducts. So
it must have the same object as F.
Yes, it has to have the same object. Yeah, so by identity objects functor, I mean both F and B are the same class of objects, and the underlying action on the objects of the functor is the identity function. So the question we're going to be interested in today is, why is there a correspondence between algebraic theories and monads at all? It's at least from the definitions, it doesn't seem obvious that these two things would be related. From the logical point of view, it's maybe more intuitive, but we're interested in the sort of purely categorical aspects. And also, we're going to ask the question, why do you even care about this? Because we need to have some motivation for a problem we're considering. So I'm going to start off with why we care about this. The first point is theoretical, that we have these two structures in category theory that are related, and it's not entirely obvious why they're related, and we're interested to figure out why, give a nice explanation, because this will deepen our understanding of category theory, which is useful. The other is more practical, which is that both algebraic theories and monads are used to express algebraic structure and variations of algebraic structure, and both are very useful in different contexts. So having a way to understand them better and then possibly generalize the situation could be very useful for doing things with different structures using category theory. So I'm going to outline a proof of the monad theory correspondence, which is new. To do that, I'm going to introduce this intermediate notion of relative monads. What is a relative monad? Well, relative monads were introduced fairly recently in 2010, and they're a variation on the notion of monads where intuitively, instead of having some structure with, we take a monad, and instead of having the underlying functor be an endofunctor, we generalize it to be any functor. So what we're going to do is fix some functor J, which acts as a kind of identity for the relative monad. And well, we're going to define a relative monad like this, but I'm not going to go into the details of what the definition is because it's not actually important for this talk. What really suffices for the talk is to just know that when we take J to be our identity functor, this definition, which looks a bit unfamiliar, actually turns out to be the same as a monad. But for this talk, it just suffices to think of a relative monad as being sort of a skewed version of a monad, where the underlying functor is not necessarily an endofunctor. What will be more important for the talk is the notion of relative adjunction, which I will define in just a moment. But the intuition is that just as a monad is induced canonically by two adjunctions, the quasi-adjunction and the Eilenberg-Moore adjunction, so too is a relative monad induced canonically by two adjunctions, two relative adjunctions, the Kleisli relative adjunction and the Eilenberg-Moore relative adjunction. And these are initial and terminal in various categories of resolutions of the relative monad. So they act in the same way as usual Kleisli and Eilenberg-Moore constructions. Now, a relative adjunction is very similar to an adjunction. So if you look right at the bottom here, we can see what looks almost like the typical definition of adjunction in terms of natural isomorphism of concepts. But instead of saying that morphisms from Lx to y are in natural bijection with morphisms from x to ry, I'm asking that they're in natural bijection with morphisms from jx to ry. So sort of skewing the adjunction along this functor j here. So when we take j to be identity, we get exactly a usual adjunction. Now, by the universal property of the Kleisli and Eilenberg-Moore adjunctions, or relative adjunctions, we get that we have a bijection between these three classes of structures: J relative monads, J relative Kleisli resolutions, and J relative Eilenberg-Moore resolutions. And by resolution here, I mean an adjunction which induces a particular relative monad. So I mean the left adjoint, the right adjoint, and the transposition operations. So first of all, we're going to take a look at the first two of these structures and sort of analyze the relationship between them. To do that, we're going to make use of this very useful characterization theorem. So if we take some functor k from A to B, which are just categories, then we have that the functor is the Kleisli inclusion for some J relative monad, if and only if the functor has a right J relative adjoint and it's the identity of objects. So this is when J is the identity, this reduces to a known sort of folklore theorem about Kleisli inclusions. But this happens to be true also for relative adjunctions. And the part I want to draw your attention to is this identity of objects part, which looks familiar because we also saw this condition appearing in the definition of algebraic theory. So sort of, we're led to consider whether we can rephrase the first condition now in terms of something more familiar as well. And to do this, we're going to make the following observation. So if we take any functor with small domain, which we'll call f, then it turns out that there's a relative adjunction. There's an adjunction relative to the Uneda embedding, which I'm denoting by yo here. So we have this relative adjunction where the left adjoint is given by f, and the right adjoint is given by the nerve of f. And by the nerve of f, I mean the restricted Uneda embedding, so precomposing the Uneda embedding by f. And this is very easy to prove. It's essentially just the Uneda lemma. And in this way, every functor from a category with small domain is a left yo relative adjoint. And the converse is also true, that if we have a left yo relative adjoint, this is the same as just asking for f to be small in a suitable sense. So really, it's a very weak condition to ask for having a yo relative adjoint. Things get more interesting when we assume that A has some class of colimits and F preserves that class of colimits. Because in this case, the relative adjunction from the previous slide restricts. So instead of just considering the pre-sheaves on A, we're considering the pre-sheaves that preserve the psi limits. So if we take for our motivating example the class of we take psi to be the small discrete categories. Then this says that every small functor which preserves finite coproducts, we're assuming the domain has finite coproducts, this functor is automatically left adjoint relative to the inclusion into the finite product preserving pre-sheaves on the domain. And it turns out that it's a well-known fact that this is equivalent to the co-completion of the domain under sifted colimits. And this is where we're starting to see some of the structures we had right at the beginning here. And the converse is also true. Every functor which is left adjoint relative to inclusion into the sifted co-completion preserves finite coproducts. So to sum up what I've said so far, we can use these facts to deduce the relationship between algebraic theories and relative monads. So in particular, we started with the definition: an algebraic theory is an identity in objects functor from F that strictly preserves finite coproducts. This is equivalent to a functor which is left adjoint relative to the embedding of F into its sifted co-completion. And hence, it's equivalent to the Kleist inclusion of a monad relative to the inclusion of F into its sifted co-completion. And this is a bit of a mouthful, and I'm going to give a simpler definition in a moment, or characterization. But what this means is that algebraic theories are in bijection with monads relative to the inclusion of F into the sifted co-completion of F. And the sifted co-completion of F is actually just a category of sets. So this is saying that algebraic theories are in bijection with monads relative to the inclusion of F into set. And F is equivalent to the category of finite sets and all functions. So algebraic theories are really the same thing as monads relative to the inclusion of finite sets into sets. Okay, so now we have a relationship between theories and relative monads, and it's essentially given by this characterization of Kleist inclusions and a sort of relative adjoint functor theorem. And now we're going to ask, what about relative monads and monads? So if we fix some class phi of weights, or like diagrams for colimits, then there's this general theorem that says that there's an equivalence of categories between the monads relative to the Unedra embedding of some category into its co-completion under phi weighted colimits, and the phi co-continuous monads on the phi co-completion of the category. So if we're taking a monad relative to the inclusion of a category into some co-completion, it's the same as looking at the monads on the co-completion which preserve those colimits. So it's a very general fact. And in our concrete setting, this means that our monads relative to the inclusion of finite sets into all sets are the same thing as sifted co-continuous monads on the sifted co-completion of F, i.e. on set, which are the same things as finitary monads on set. And so in this way, we capture the relationship between theories and monads going via relative monads. Now I appreciate this is quite a quick way to give the proof, but what I want to note is that the argument is very elementary in that we don't, for instance, use any monadicity theorems, which are usually used in proofs of monad theory correspondences. And so we're really just looking at the definitions of the structures and making use of characterization theorems to move between the different ways of seeing the data. Now, if we're sort of proposing this as a nice way to look at monad theory correspondence, then we'd really like it to be quite general, in that in the literature there are many generalizations of the classical monad theory correspondence that capture things like enrichment and more complex structure than just finite coproducts. And so we'd like to know whether this method can be applied to more general classes of theories and monads. So again, we're going to try doing this, but with more general definitions of theory. So it will turn out that theories can always be related to relative monads for some suitable definition of theory, for at least for those relative monads for which the functor J is dense. That's going to be essentially the only assumption we need. And relative monads can be related to monads a lot of the time, not all of the time. So if anything goes wrong with a monad theory correspondence, this is where it's going to break down. But in most of the settings we care about, these assumptions are going to be very easily satisfied. So now I'm going to fix a functor J. I'm going to ask for it to be dense. I'm going to say that a J theory is an identity on objects functor from A, which has a right J relative adjoint. You can see this is very close to the definition of algebraic theory from before. I'm going to call the theory J the category of J theories, which is the full subcategory of the slices, the co-slices under A on the theories. So what this means is that the morphisms of J theories are commutative triangles. This is just the same as the morphism of algebraic theories. And the theorem is that under these assumptions, which are essentially no assumptions at all apart from density, we have an equivalence between the J theories and the J relative monads. So getting to monads is a bit more complicated. So we know that when J is the inclusion of a category into some co-completion, then we can use this theorem from before, which says it's the same as some class of relative monads. But we're really interested in more general J. So what we're going to do is define a couple of new concepts. So we want to identify when a monad is essentially the same as a relative monad. And what does it mean for a monad to be the same as a relative monad? Well, what we really care about is the algebras. So if the algebras are the same, then we're going to relate the monad and the relative monad. So we're going to say that a monad, we're going to fix the functor J as before. I'm going to say a monad on the codomain of J is J-ary if there exists a J relative monad with the same algebras. And by the same algebras, I mean that the categories of algebras are isomorphic, and the isomorphism commutes with the forgetful functors to the base category. And conversely, we're going to say that a J relative monad, T prime, is realizable if there exists a monad with the same algebras. And sort of almost by definition, we can see that if there is a J-ary monad, then there must be a corresponding realizable J relative monad, and vice versa. So these two things are essentially the same. And so we can prove there's an equivalence between the realizable J relative monads and the J-ary monads, and this commutes with taking the categories of algebras. And one thing I want to note, because it sort of makes it very easy to tell how this equivalence is formed, is that the functor that takes a J relative monad to its corresponding relative monad, takes a J-ary monad to its corresponding J relative monad, it's given just by precomposing the monad with the functor J. So precomposing the underlying functor and also the natural transformations that form the structure. There's always sort of a canonical candidate for a J relative monad for every J-ary monad. And in suitable conditions, we can characterize the realizable relative monads and the J-ary monads. So instead of having this very abstract definition, we can have a nice characterization of all the monads that satisfy this property, like the existence of some J relative monad. And this will be used for the general correspondence. So first, we're going to look at the realizable relative monads. The relative monads that can be sort of extended to a monad. And there's a very nice characterization result, which says that if the forgetful functor from the category of algebras of the relative monad has a left adjoint, then the induced monad of this adjunction corresponds to the relative monad in this way. So the relative monad is realizable, and the induced monad is J-array, and the two correspond under the equivalence. So realizability is essentially just an adjointness condition. For characterizing the J-array monads, I need to introduce one more concept, which is that of a J absolute colimit. So a colimit in E, i.e. the codomain of J, is J absolute if it's preserved by the nerve of J. So remember, the nerve of J is this restricted unadra embedding where it's precomposing by J. So if that functor preserves the colimit, I have this isomorphism at the bottom, where I'm using a semicolon for diagrammatic composition, then we call the colimit J absolute. And to give some examples of J absolute colimits, when J is the inclusion of a category into its co-completion under some class of colimits, then that class of colimits, each of the colimits in that class are J absolute in particular. So like if we're taking the co-completion under filtered colimits, and the filtered colimits are J absolute. And when J is the identity, the J absolute colimits are precisely the absolute colimits. And absolute colimits are those that are preserved by every functor. So we do recover the classical motion of absolute colimit using this relative definition. So now we can characterize the J-array monads in nice settings. We have a few more assumptions here. So we have to, okay, when I say admissible, it's really a smallness condition that I'm not going to define precisely, but it's satisfied, for instance, if the domain of J is small, but also in slightly more situations. The important thing is that we ask for J to be dense, and then we suppose that we have pointwise left Cartan extensions along J, and that these Cartan extensions are J absolute. In this case, which is satisfied in most situations we care about, we have that every J relative monad is realizable, and we can characterize the J-array monads to be those which can be expressed as this Cartan extension, or as just those monads that preserve the J absolute colimits. And this way we recover the classical monad theory correspondence again, because when we take J to be the inclusion of category into its sifted co-completion, this just says that T preserves sifted colimits. So it's a sifted co-continuous or finitary monads from before. So from these conditions, we can form a general monad theory correspondence. So again, we have J satisfying the same assumptions as the previous slide. And in these conditions, we have an equivalence between the J theories and the J-array monads, where the J-array monads are those preserving J absolute colimits. So one thing to note here is that this equivalence captures a very large class of examples of monad theory correspondences in the literature, but not all of them. And so when I say general with this star, it's general, but it's general under the assumption that we want to have nice characterizations of the J-array monads. But we can weaken these assumptions further as long as we're happy getting slightly more tautological characterizations of the J-array monads. In some concrete settings, maybe we can give a better description of the J-array monad, so that's not a bad thing. And in fact, it is necessary to weaken these assumptions to capture some of the examples in the literature, such as the correspondence of John and Richard Garner.
That was the motivating example, in fact, for our paper requires that extension, if you like.
Thanks, yeah. So, yeah, I'm going to come back to that at the end as well. Okay, so if you are familiar with the monad theory correspondence, you might have noticed that I've sort of skipped something, which is that when we talk about the traditional monad theory correspondence, there's an extra property we expect, which is that when we take an algebraic theory and look at its category of models in set, these are equivalent to the algebras for the corresponding monads. And so far, I haven't talked about algebras at all. And so in the classical arguments for monad theory correspondences, or at least many of them, where one uses a monadicity theorem, you can't you can't explain the monad theory of correspondence without using algebras because they're part of the proof. But somehow we've got to correspondence without talking about algebras, so now we need to add them back in afterwards. So let's think about those. So to talk about the model algebra correspondence, we're going to use the following theorem. So we're going to take some functor j, as before, and we're going to ask that it's dense and also satisfies some smallness condition, so the definition of admissible means that we can form this nerve. That's the definition. But it can be rephrased in other ways. And then we're going to fix some j relative monad T. In this case, there is a pullback square. And then we step through the pullback square. So on the right-hand side, at the top right, we have the pre-sheaves on the Kleisy category of T. On the bottom right, we have the pre-sheaves on A, which is the domain of J. And the function on the right is given by precomposing the Kleisy inclusion, which is denoted here by KT. On the bottom, we just have the nerve of J. And so when we take this pullback, we get exactly the category of algebras for the relative monad. And the sort of conceptual way to think about this is that the Eilenberg-Moore category is given as some kind of co-completion of the Kleisy category. And from monads, this is sort of very well known because we can form the algebras from monad from the free algebras by taking quotients, essentially by adding in equations to the algebras. And so this theorem sort of expresses something similar to that. It says that we can form the normal algebras by taking some class of colimits of the free algebras. Now, when we take J to be identity, the nerve of J is just the Unedra embedding. And we get the category of algebras from monad is the pullback over this Unedra embedding and the precomposition by the Kleisy inclusion. And this observation, I would say, is still not very well known, but it is in the literature, and it's due to Linton. And the nice observation is that this extends very nicely to relative monads. And we'll see why this is at all useful in just a moment. So we know from the first part of the talk that J theories or algebraic theories are essentially the same thing as Kleisy inclusions for relative monads. And so where I have the Kleisy inclusion for a relative monad here, if I have a theory, the Kleisy inclusion is just the theory. So if we again fix J to be such a functor, and we let K be a J theory, and we denote by T the monad that is induced or corresponds to K, then we have the following pullback square. And this is just using the pullback theorem from before and the relative monad theory correspondence. So here the pullback is the same, except on the right we have just the functor between pre-sheaf categories induced by precomposition. And what we're going to do is we're going to define the algebras or the models for a J theory to be the apex of this pullback. And in this way, the correspondence between models for an algebraic theory or algebras for an algebraic theory and algebras for relative monad is tautological. But what we do need to show is this captures the classical notion of model for an algebraic theory if we do this. This is actually very straightforward to show. Because if we consider L an algebraic theory, which is the same thing as a theory relative to the inclusion of finite sets into all sets, and we denote by TL the relative monad that corresponds to L, then from the previous theorem we have the following pullback. And we said before the category of sets is the same thing as the finite product preserving functors from F op intercept. This is just the universal property of F. And then it's easy to show that because we have two pre-sheaf categories on the right and we have a finite product preserving pre-sheaves on the left, that the apex must also be a category of finite product preserving functors. or presheaves. And in particular, it's a finite product preserving presheaves on L, which is the codomain of our algebraic theory. And this is exactly the category of models for an algebraic theory. So from this pullback characterization of the category of algebras for a relative monad, we get the classical definition of model for an algebraic theory. And this sort of justifies our definition of algebra for an algebraic theory as this pullback. And yeah, if you're familiar with work on monad theory correspondences, essentially the same pullback appears in several other papers, and this gives a sort of conceptual justification for why it's a theorem. So in other words, the models for an algebraic theory coincide with the algebras for the corresponding monad due to this pullback characterization of the Eilenberg-Moore category. Okay, so near the start, I said that the universal properties of Kleisli resolutions and Eilenberg-Moore resolutions meant that both were in bijection with relative monads. And so in the first half of the talk, I just considered Kleisli resolutions. But now we can ask the same question about Eilenberg-Moore resolutions. Because if we get the monad theory correspondence from just relative monads and Kleisli resolutions, do we get anything interesting from the Eilenberg-Moore resolutions? So that's going to be the topic of the second half of the talk. And to answer this question, we're going to start off with the following. We're going to generalize the monadicity theorem to relative monads. So we're going to fix a dense functor, J. So density is essential here. In this case, we have the following two conditions being equivalent. So the first condition is that we're fixing some functor R from into the codomain of J. So the following two conditions are equivalent. The first is that the functor R creates small j absolute colimits and has a left j relative adjoint. And the second condition is that R is j relatively monadic. And by that I mean that R is the forgetful functor from the category of algebras for a relative monad, at least up to here. I'm thinking about strict creation of absolute colimits. So I'm asking for it to be isomorphic to the category of algebras for a relative monad over the base category. Now, one thing you may notice is this doesn't look exactly like the classical Beck monadicity theorem, where we ask instead for this creation of U split coequalizers, or in this case R split coequalizers. And that's because this is really a Paré style monadicity theorem, where we're interested in absolute colimits rather than U split coequalizers. But they turn out to be the same, and for relative monads, the Paré style theorem is more appropriate. Now we're going to define a notion of theory and for the Eilenberg-Moore resolution, analogous to the notion of theory for a Kleisli resolution. So fixing J, a dense functor again, we're going to say that a J-op theory is a functor into E, which strictly creates small j absolute colimits and has a left j relative adjoint. And so really, I'm just reading off the conditions for a functor to be relatively monadic. And we're going to say the category of op theories is the category of these slices into E. So the morphisms are just commutative triangles, like with theories. In this case, using the monadicity theorem, there's an equivalence between the category of relative monads, the J relative monads, and the category of J-op theories, or the opposite of the category of J-op theories, and hence also the category of J theories. And how do we think about this conceptually? Well, we think about it as a sort of duality, in that theories and op theories are the duals of one another. because theories axiomatize the Kleisli inclusion for relative monads, because Kleisli resolutions are initial, and the opt theories axiomatize the forgetful functors from Eilenberg-Moore categories of relative monads. And Eilenberg-Moore resolutions are terminal. And so it's kind of initial terminal properties of these two structures. So on this slide, I noted that the theories and the J theories and the J opt theories are dually equivalent to each other. But to prove this, we go by the equivalence to relative monads. And one thing we can ask, and maybe it seems slightly unmotivated, but we'll see that it's a very fruitful question to ask, is what happens when, what can we say about passing from a J theory to its associated J opt theory, and vice versa? So what can we say about this passage, sort of skipping over the J relative monads, going via them, but sort of disregarding what the J relative monads are? And is there anything interesting we can say about this? And this is going to be the final part of the talk. Okay, so as always, we're fixing a dense functor J, and we're going to find these two concepts. So an A pre-theory will be a functor, just some functor from the domain of J, which is the identity objects, and an E pre-op theory will be a functor into E, into the codomain of J, which strictly creates small J absolute codomains. And the thing to notice here is that the pre-theories and the pre-op theories exactly become the theories and op theories when we add the jointness conditions. So you just sort of remove the relative jointness conditions from theories and op theories to get the definitions of pre-theory and pre-op theory. And the terminology pre-theory here is coming from the work of John and Richard Garner, but it also appears in Linton's work as an A clone. So this has some relationship to abstract clones as well. So when algebraic theories were introduced originally by Levier, one of the theorems he proved was something which later came to be known as the structure semantics adjunction. Here, I think I'm using the dual form. I've taken opposites on both sides. My left adjoint is the structure. So apologies if that's slightly confusing if you're familiar with this junction already. But what is the structure semantics adjunction? Well, we're considering the category of algebraic theories. The objects are algebraic theories, the morphisms are the commutative triangles. And we're considering the category of functors, well, functors into set, and the morphisms of commutative triangles. And the left adjoint is going to send a functor into set to the algebraic theory whose operations are formed by natural transformations. So if we have some functor u from x into set, we consider the natural transformations from un into u. And it turns out this forms an algebraic theory. And in the other direction, if we have an algebraic theory, we can look at the forgetful functor from its category of models into set. And this is just a functor into set. So it works out. There's a star here because there are some size issues we need to worry about if we're doing this precisely. I'm not going to go into the details, but that's why that's there. So how do you think about the structure semantics adjunction? Well, the idea is that algebraic theories represent algebraic structure, and the category of slices is representing forgetful functors. But the forgetful functors may not really be forgetful functors from categories of algebras. But sort of the structure functor is giving us the best approximation of an algebraic theory from a almost forgetful functor. And so in particular, if we have an algebraic theory, look at its forgetful functor, and form an algebraic theory from the forgetful functor, we get back the original algebraic theory. But we can start with something that's not quite a forgetful functor and get an algebraic theory out. And so it's it's a way to pass between, well, the name comes from, the structure is the algebraic theories, algebraic structure, and the semantics is how we're interpreting the categories of models. And so the structure functor takes some maybe category of models to the structure that's associated with it, and the right adjoint takes a category of algebras to its semantics instead. And this is it turns out to be very useful. It comes up in lots of places when you're thinking about algebraic theories and monads. It's a very, very nice observation. What's even nicer is that a few years later, Linton provided quite a large generalization of the structure semantics adjunction, which I think has been essentially overlooked. So the adjunction here is entirely due to Linton. We're going to fix the functor j as before. We don't need it to be dense. But for size issues, now we're going to ask that both a and e are small, and this can be, we can lift these assumptions, but it becomes more complicated. So for now, I'm going to make a simplifying assumption. In this case, we have an adjunction between the category of co-slices under A and the opposite of the category of slices over E. And I'm not going to go into too much detail about why the adjoints are defined as they are, but I can give a little bit of intuition. So the left adjoint is going to send a functor k, so k is a functor from A, into this left side that's pullback. And the thing to notice about this pullback is it looks very similar to our definition of the category of models for a J theory. It's essentially the same pullback, but we're not requiring K to be a theory here. And on the bottom, we have this more complicated situation. I should really rewrite it. I should have really rewritten it because we can really think of this as being, we can write it in a Homset notation that looks slightly nicer, where we have J and U. But I mean, it's not important to know exactly what the functors are. The important thing is there is this adjunction for the purpose of the talk. Okay, in particular, this is also due to Linton, we can pre-compose another adjunction between the pre-theories, i.e. identity object functors from J, and the category of co-slices under A. And the proof of this is just using the identity objects fully faithful factorization system on CAT. It just gives us this adjunction very easily. And so in particular, actually, there's one more thing I wanted to say. Okay, so now we have an adjunction between pre-theories on A and the opposite of the category of slices over E. And the new observation is that this adjunction, when we look at the left adjoints, the image of the left adjoint takes values in pre-op theories. So if we start with a pre-theory, and we apply these two left adjoints, we get a pre-op theory out. And so this means we can restrict this adjunction slightly and say more precisely that this adjunction is an adjunction between pre-theories on A and the opposite of the category of pre-op theories on E. And we can call the left adjoint the semantics function, the right adjoint the structure functor. And I mean, they're still given by these assignments. But now we can see that if we look at at least the right-hand side of the left adjoint, when K is a J theory, we know that this pullback defines the category of algebras. And so we know when we start with a pre-theory, it's a J theory, we will get a J op theory out. And it turns out the converse is also true, with a little more work in the other direction. And so this adjunction restricts to an adjoint equivalence between the J theories and the J op theories. And this way, we've entirely sidestepped the relative monads. We've gone directly from J theories to J op theories. And in this sense, maybe maybe one can say that the J relative monads are given by fixed points of this structure semantic disjunction. And that's how they sort of arise. That's one motivation for relative monads, is they arise as fixed points of this structure semantic disjunction. So just to give a big picture for what we've shown, at the top we have the theory relative monad correspondence and the op theory relative monad correspondence. These embed into the pre-theory, pre-op theory structure semantic disjunction, and these all commute with taking categories of algebras. Under suitable assumptions on J, on top of density, we also get correspondence with monads as well. But often the very nice conditions for the J monads aren't satisfied, so I didn't include in this diagram because I wanted the very simple assumptions for this one. So just before I end, I want to give more concrete motivation for this this work, because in a sense it's very nice that we have this abstract understanding of the monad theory correspondence via relative monads, which does explain quite a lot of the definitions that come up in the literature in a new way. But is it actually useful? Is a reasonable question to ask, because one of the motivations at the start was that we use algebraic theories and monads a lot in category theory. So if we have a general theory, we'd like it to be useful for something. So first of all, is it useful? And for instance, do we get any new examples of monad theory correspondences? That would be a valuable consequence of this work. So I want to mention that although for the talk I've really been just talking about ordinary categories, all of the theory works for enriched categories. And in fact, we can use a very general base enrichment. So in our setting, we're actually working with categories enriched in the bi-category with some completeness and co-completeness assumptions. Why do we work with enrichment in the bi-category? This seems maybe overly general, but actually it is useful because there are examples in the literature of theories that we can capture which aren't captured by other frameworks, monad theory correspondences. And we also can subsume the other correspondences in the literature which have different forms of enrichment, including enrichment in non-symmetric monoidal categories. And non-symmetric monoidal categories are essentially bi-categories for the purpose of enrichment. Okay, so our first class of examples. This will be familiar to you if you're familiar with monad theory correspondences. If you're not, then don't worry. It's just some correspondence in the literature. But in particular, Lucian Wright in 2016 developed a general monad theory correspondence for enriched categories with respect to what he calls an eleutheric system of varieties. So he has a notion of J theory, which is ostensibly different from ours, but one can prove that his J theories are the same as J theories in our sense, and are hence the same as J relative monads. And it turns out in this case that Lucian Wright's monad theory correspondence is subsumed by ours using this lemma. Another class of examples is that of John and Richard Garner, who developed a monad theory correspondence with respect to a dense fully faithful functor with small domain and locally presentable codomain. And it turns out that one can show that an A theory in the sense of Burke and Garner is precisely a J theory in our sense, and hence also J relative monads. And their nervous monads are the same as our J-ary monads. And so in this way we capture that correspondence as well. For some new examples, coming from computer science, Tony Hoare developed a framework for data refinement sort of in a type theoretic setting, and this was rephrased for categorical setting by Kinoshita and Power, who showed that you could do his theory if you enriched in a particular non-symmetric model category of locally ordered categories. The important thing to note here is that we're enriching in a non-symmetric monodal category, and which means in particular it's not captured by other frameworks for monad theory correspondences. But it is captured by our framework because we can treat this non-symmetric monodal category as a one-object bicategory, and it satisfies the assumptions we need. The more interesting example is that Johnson and Wraith in 1977 developed a monad theory correspondence for monads on internal categories, so internal monads, and an internal notion of algebraic theory for some topos E. So algebraic theory is internal to topos E. And surprisingly, if you haven't heard this result before, I think it's a very beautiful result that you can capture internal categories under suitable assumptions by enrichment in a bicategory. So if we enrich in the bicategory of spans in E, then we can recover the internal monad theory correspondence. So this is sort of the main motivation for bicategory enrichment. We can capture internal monad theory correspondences. So just to summarize what I've talked about, because I've gone through everything very quickly, the idea is that the way we'd like to view the monad theory correspondence is the combination of two phenomena: the relationship between theories and relative monads via this quasi-characterization, and the relationship between relative monads and monads with the same category of algebras. And in this way, the definition of the category of models for an algebraic theory is a consequence of this pullback characterization of the Eilenberg-Moore category. The structure semantics adjunction from classical categorical logic is really about the relationship between pre-theories and pre-op theories. And in this way, we can cover the monad theory correspondence. And the justification for this perspective, or one justification for this perspective, is that we can use it to capture the existing monad theory correspondences in the literature. So it's general enough to do what we wanted to do. I've got some references here, and I'm going to stop there. Thank you.
All right, thanks very much. Very nice talk. Any comments or questions?
Yes, I have one.
Yep.
You seem to be unaware of the definition. Oh, no, so you're not, sorry. I just wanted to say your reference number 1 is the first place where relative monads were defined, but you are not unaware, so.
Yeah, so I said it very quickly. I probably glossed over it a bit too quickly. I said relative monads were first defined in 2010. Yeah, that part is not new, and neither is relative adjunction, which is from even earlier due to Ulmer. Yeah, so we're using their definitions.
Okay, and then just one small comment. I was surprised when you several times used the phrase, the categories of algebras of two monads are isomorphic, and then you had to explain that it's actually a commutative triangle. Why not say the two monads are isomorphic, which is the same thing?
Because we want to say when a relative monad is isomorphic to a monad, but it's very hard to say what a relative monad being isomorphic to a monad is unless we have some sort of category in which both relative monads and monads exist. And I didn't really want to get into that here, so it was easier to use the definition in terms of isomorphisms of categories of algebras over the forgetful functors, and just replace one of the categories of algebras with a relative monad. So sort of taking advantage of that result to avoid questions of when is a relative monad isomorphic to a monad.
Okay, thanks.
Go ahead.
So maybe it's a naive question, but as far as I understand the classical notion of an algebraic theory, that corresponds to a finite product sketch, because it's just a category, and the finite product cones are just the images of the components from finite set. So is it possible to say something about which extended class of sketches J theory corresponds to?
Yeah, I don't know is the answer. So it's certainly not the case that every kind of limit, co-limit sketch can be expressed this way. And I'm not sure about the converse. One thing to note is that some of our J theories can be expressed using either limit or co-limit preservation properties, but not all of them. And so you'd have to use a more general notion of sketch than a limit co-limit sketch. But there are more general notions of sketches, and maybe one of those would work. Yeah, I don't know.
Gabriella, you have a question?
Yeah. I mean, thanks for the talk, first of all. And secondly, yeah, when you were talking about realizable relative monads and monads, and you define them using this equivalent, this isomorphism of the algebras. My question is, what happens if you require an isomorphism of the Kleisler things, categories?
So in general, that's not enough. I think when there are additional assumptions you can add to J, which makes that a sufficient condition, but in general, it's not enough. And so the right definition is in terms of the algebras, but as a lemma, you can also have that the Kleisler categories are sometimes enough. And this is, you can even see hints of this in the original work on relative monads, this 2010 and 2015 paper, where they talk about monads corresponding to relative monads, and they show that under their assumptions, which are already quite strong, the Euler-Vermor categories coincide and not the Kleisler categories.
Yeah, when you say it's not enough, like what is the problem? Like what is missing in the proofs and stuff? Yeah, I mean, if you thought about it.
Yeah, I can't remember off the top of my head. I would need to remind myself.
Thanks.
Yeah, it's a problem with the free algebras not capturing. So I guess intuitively the problem is that when you have a Kleisler category, the objects of the Kleisler category are just coming from the domain of J, i.e. the category I was noting by A, whereas the category of algebras are given by objects of E. And so intuitively, if A is a lot smaller than E, or if A doesn't contain all the structure of E, you can't capture all the information about algebras in E from A. So it works for identity, for J, the identity, i.e. regular normal monads, because A and E are the same. But in general, A and E can be very different, and J might not be very nice. And so intuitively, that's the reason why it doesn't work.
Thanks.
Maybe I'll mention that. So Marcelo Fiore, Richard Garner, and I had been working on some related stuff, and we proved one of the things we did was the monadicity theorem for relative monads. That was what we were working, but we didn't do nearly so much as you've done about all the other stuff. But yeah, it's really like I think it seems probably the right story if you want to, remove co-completeness assumptions and things like that. You have to work with relative monads, and it seems like it's a nice story. Any more questions? Well, if not, then let's thank Nathanael again. And so next week we have Jan Jurka will be talking about a cone small object argument. So, okay, so that's it for today. Thanks for coming.